clearance is not looking used.
We have main engine start. 4, 3, 2, 1, and liftoff.
Challenger going into the shuttle mission will launch. My God.
Why is that funny?
It's like, my God.
Jose the science guy. Jose the science guy. Jose the science guy. Science ruler. Jose the science guy. Jose the science guy.
Hey, I'm Jose the Science Guy, and you just watched footage from the famous Challenger disaster that changed the space program forever. After careful analysis, scientists and engineers figured out the disaster was caused by a failure in the O-rings, a rubber ring designed to seal fuel in the solid rocket boosters. Here to talk more about this is Mian and Elliot.
As you may or may not know, a standard space shuttle has 4 components. The 2 solid rocket boosters, the external tank, and the orbiter. The solid rocket boosters have rings on the outside that keep the fuel inside. The O-rings are naturally able to keep fuel inside at a normal temperature. However, the Challenger was launched on a particularly cold day. In fact, 15 degrees Fahrenheit, colder than any previous launch. Many people at NASA, including the astronauts, did not think the launch would occur on that day. Some engineers even refused to sign the safety papers. Surely enough, these cold temperatures prevented the O-rings from expanding, thus allowing fuel to leak and causing an explosion.
Please, consider the following. Hey! So, we're going to demonstrate to you how the O-rings failed with a little experiment you can do at home. Here's what you'll need. Try this. Get 2 cups. Fill one with ice water and one with room temperature water. Get 2 O-rings or a piece of rubber. Next, contort the rubber. Then hold the position with a clip. Then place 1 O-ring in each of the cups and wait about 5 minutes. Take the rubber out of the water. The room temperature rubber still has decent resilience. See, the cold rubber has lost all of its resilience. Hey, that's pretty good. Thanks for considering the phone.
These explosions could certainly have been avoided if the shuttle was launched on a warmer day. The O-rings would have worked as they should have, and as they did in previous and following launches. Even so, it is good to have precautions against such conditions. For instance, we could have used a different substance.
Silicon is much more resistant to the cold than fluorocarbon rubber, but it has a narrow temperature range, and it is not very resistant to fuel.
Hey, didn't see you there. So there are some pros and cons to the fluorosilicon rubber compound. Here's Jude to talk about it.
As mentioned before, silicon is resistant to the cold, but not to fuel, which is the problem. Fortunately, fluorosilicon rubber, a blend of silicon and fluorocarbon rubber, is both resistant to fuel and cold. Fluorosilicon rubber is not the only material that could replace fluorocarbon rubber. Other synthetic silicon rubber compounds would also work.
These properties make fluorosilicon rubber ideal for our O-rings.
So, what did we learn today? We learned that organic rubber compounds can lose their properties in cold temperatures, silicon is resistant to the cold but not fuel, and that rubber and silicon compounds can combine the properties of both to create a compound that is resistant to the fuel and to cold.
Cool. I think we learned a lot today. See you next time on Jose the Scientist. Yay!
You deserve some. 10 out of 10. 10 out of 10, honestly.
Questions, guys?